All right, so we're fortunate to have Ilya Razenshteyn today. Ilya truly works in all areas of computer science, from theory to machine learning, data analysis to security. And Ilya is a world expert on nearest neighbors and has also applied this problem in all possible contexts with like various applications in other areas. And today he is going to present applications of nearest neighbors for optimal transport.
Thanks, Sasha, for the introduction. So I have 1 hour, right? Just to be clear, until 11. Awesome. Okay. I will talk about our paper where we try to approach the problem of nearest neighbor search for the optimal transport distances. I will explain what nearest neighbor search is, and I will explain what optimal transport is. But the talk is based on a joint work with Artur Zbachkurs from TTI Chicago, Yihe Dong, who is at Microsoft, Piotr Indik, who is at MIT, and Tal Wagner, who is at Microsoft as well. And the paper appeared at this year ICML. And the links, you can see the link to the archive preprint, and also we published a code that you can try out. It's on this GitHub link. Okay, let me start with optimal transport. And the one slide introduction of it is pretty much this picture. So this is like minimum cost matching. So what we did here is, suppose that we have a bunch of red and bunch of blue points on the plane, and we would like in some sense to measure the distance between these sets. So there are many ways to formalize what do we mean by distance between these sets, but one popular way of doing it is just like, let's compute minimum cost perfect matching. So let's try to match red to blue points in a way that we minimize sum of distances, sum of Euclidean, for example, in this case, distances. And this is the optimal matching for this specific configuration of points. If you haven't seen how to compute such a minimum cost matching, actually, it's not a priori obvious, because a priori you would need to enumerate n factorial combinatorial configurations. But any of you who is sufficiently spoiled with CS education, and I suppose it's all of you here, there are efficient algorithms. You can write it down as a linear program and solve it, or there are faster combinatorial algorithms for this problem. I will talk more about it a bit later. So my talk will be about certain generalization of this simplistic picture. The object is called Wasserstein distances, and let me explain what this means. So this is more or less obvious generalization of this matching from the previous slide, but now instead of having the same number of red and blue points, we can have different number of them, and moreover, we will allow weights. So basically, it's convenient to think about two distributions. We have one probability distribution over red points, and one probability distribution over blue points. So on this picture, basically the brighter the point is, it means that the less mass there is put there. And then we are trying to match these probability distributions again in a similar way. So we kind of want to move red points to the blue points, and the amount we have to pay is distance times the amount we are moving. So this is pretty much definition of Wasserstein distances. Let me be slightly more precise, but pretty much I told you the definition already. But the formal definition is the following. So we have underlying metric space. In this case, it's plane with Euclidean distance. And we have two distributions, mu1 and mu2. And for the sake of this talk, we will assume that they have finite support. In some other applications, it's convenient to think about continuous distributions as well, but let's not worry about it. Basically, we assume that mu1 and mu2 are distributed among distributed across finite number of points each. And our goal is to find basically distribution over product of two copies of our metric space, such that on one hand, marginals of this distribution are exactly our distribution mu1 and mu2. And we are trying to minimize this functional that is on the screen. So basically, we are trying to minimize, with respect to this joint distribution, we are trying to minimize pth power of the distance between the endpoints. And basically, it's easy to check that. So basically, in the informal definition I gave you, p was equal to 1. But we can, in principle, consider other values of p. For example, p equals 2 is a very popular choice. So it's not easy. Sorry, it's easy to check that this pth Wasserstein distance is a metric between distributions. And my talk will be focusing on p equals 1. So it has some further nice properties. For example, it can be realized as a norm in some sense, but it's not going to be important for our talk. So let me just emphasize one last time. So there are two metrics here. There is, first of all, underlying metric space. In this case, this is Euclidean space on a plane. And then we consider distributions on this space, and then we equip these distributions with a new metric, which we call Wasserstein P metric, which is defined as I just told you. And basically, it is this metric, it is this new metric space that will be of the main interest for us. So underlying metric can be easy, but this like Wasserstein P metric space can be fairly complicated, as we will see later in the talk. Okay, so this is Wasserstein distances. And before solving the nearest neighbors with respect to it, let me even motivate like why on earth would we possibly care about such a problem. And this was actually directly motivated by applications. We didn't really invent this problem. There was like a need for it, and as I will demonstrate now. So basically, Wasserstein distance or earth mover distance historically was used a lot for computing similarity between certain structured objects. So for example, there is this classic paper back from 2000 by Rubner, Tomasi, and Guibas, who applied earth mover distance for computing similarity between images. So basically their way of measuring similarity was, suppose that I have two pictures and I want to understand how similar they are with respect to colors. So how colorfully similar, like how similar they are from the colors point of view. So what they said was, let's represent each picture as a distribution in a three-dimensional space. So basically they consider color space. So basically like 256 by 256 by 256 kind of cube. And then like each image can be represented as like distribution over its pixels there, right? And then they kind of showed empirically that earth mover distance between these distributions, I don't know what underlying metric they considered, Euclidean or L1 metric or whatever. But they said that this is like, they argued and they established with experiments that this is a good similarity measure between images. And so this was good. But recently there is a new surge in interest for optimal transport. And it comes in particular from this paper by Kushner, Sun, Kolkin, and Weinberger, who actually showed a very cute application of earth mover distance to measure similarity between text documents. And let me talk a little bit more about it because it will be central in this talk, this application. So suppose that I would like to understand the similarity between two sentences or two maybe paragraphs of text. For example, we can look at these two sentences on the screen. Modulo stop words, they don't have any common words, right? So for example, classic approaches like bag of words model or something like this, they wouldn't be able to tell that these are similar sentences, right? Even though we kind of understand that it means the same. At least it meant the same in 2015 when Obama was still a president. This is an example from this paper. But how can we capture that these are the same sentences? And there are many ways to do it. People just use neural networks for it. Like, you know, we can pass this sentence through neural network and obtain a certain feature vector and just compute distance between feature vectors. But in this Kushner et al. Paper, they take kind of related but slightly different approach that I'm going to tell you now. So they just say that, okay, let's take word embeddings. So what is a word embedding? It's a mapping from words to a relatively high dimensional space, for example, word to vec or glove. There are like many other approaches for that. And intuitively, what we require from this word to vec embeddings is that semantically similar words get mapped into closed vectors. So, okay, so great. But after we have such a mapping, we can consider each sentence as a distribution over the respective word embeddings. For example, first sentence would be distribution over 4 blue points, and second sentence would be distribution over 4 black points, right? And then we compute minimum cost perfect matching. Or if it's like different number of black and blue words, we can just compute, you know, like earth mover distance or Wasserstein distance, basically fractional matching. And they showed that this is a very good similarity measure. So in the following sense, so they show that if you just do k nearest neighbor classification with respect to earth mover distance defined as I just told you, then actually this is good for solving various classification tasks. For example, type of classification tasks they solved was, you know, given Amazon review, try to understand which topic is it, right? And stuff like that. So basically they evaluated a bunch of these tasks and realized that this earth mover distance measure is superior to all the other alternative proposals. Okay, this is great, and this directly motivates k nearest neighbor search with respect to earth mover distance. Basically, even this paper already realized that this is a computational bottleneck. So basically, if we have any significant number of text documents, then actually searching k nearest of them with respect to Earth mover distance is fairly expensive. And the formal problem we are solving here is k-nearest neighbor search. Yeah, so basically, let me give you a quick reminder what this is. So we have n distributions over d-dimensional space, and this is our data set. And then we have a query distribution, and then we would like to find k closest distribution with respect to Earth mover distance. By the way, can you hear me? There is some kind of weird noise outside. I'm trying to understand if it affects. Okay, awesome. Great. So this is our problem. And this is, again, like very standard problem in the literature, k-nearest neighbor search. Usually people consider it with respect to Euclidean distance or L1 distance. But here the twist is that we would be considering this optimal transport distance. Again, this problem was studied in the literature already. This Kushner et al. Paper kind of raises this problem, and they propose some solutions, which we will discuss, even though these solutions end up being, like, it's possible to improve upon them by a lot, as we will see. But yeah, so basically this is directly driven by applications. That's what I wanted. That's the point I wanted to drive across. So let's start with trying to solve this problem. So the first, always, like, you know, if you have nearest neighbor search problem, the first naive thing you can do is to try to solve it exactly and in a straightforward way, right? So suppose that we would like to compute just, like, you know, n Earth mover distances, right? So how can we possibly do this? For example, if you have Euclidean nearest neighbor search, you just compute a bunch of Euclidean distances, trivial, right? And that's actually already pretty fast. But here, the computational problem is much more interesting because just even computing individual EMD instance is, like, far from being obvious. And again, I kind of, like, hinted at it in the beginning of my talk, but there are essentially, like, two kinds of approaches. First of all, if you don't care about efficiency, you just want it to be solved in, like, polynomial time, you can write down a linear program and solve it. But in practice, this is a bit too slow. So what we can do, sorry, just give me a second, let me close the window. Okay, sorry about that. If we are not happy with the performance of linear programming, what we can do is we can use specialized algorithms for minimum cost flow. For example, a very good option that actually works super fast in practice, it's like network simplex, which was invented by Cunningham in 1976. But in any case, so this is roughly the landscape of approaches. If you want to compute flow exactly, we either use linear programming or specialized combinatorial flow algorithms. Okay, so far so good, but this is still slow. Yes, I see there is some question.
Yeah, so
yeah,
the linear program is only good for your L1 norm, right?
No, actually it doesn't matter because you can, so basically, okay, so let me say in half a minute, how do we write a program? So basically variables, we have how much flow we move across every edge. And then we have constraints such as, like, you know, the whole red point should be moved to a blue point should not receive more mass than its weight. And then we can just, like, assign any cost. It doesn't have to be L1, it doesn't have to be metric even. It can be any, it can be positive, it can be negative. It literally can be any cost matrix, yeah.
Okay, thank you.
And actually, like, it's a very good question in the context of next two slides, in the sense that people need such matching computations, and then they realized that they're slow, so they invented many ways to actually, like, speed it up, right, at the cost of some approximation. And basically, approximation are divided into two groups. The first group is, I would call it non-metric case, where, like, exactly, cost matrix between red and blue points can be anything. It doesn't have to come from a metric, it doesn't have to come from a nice metric, let alone. It can be literally any matrix. Maybe sometimes we require that it's non-negative, but that's pretty much it. So suppose I want to compute now my Earth mover distances approximately. Suppose I still want to do linear scan, but instead of exact computations, I want to do these faster distance computations. So what can I do in that case? There are, again, many approaches, and this is, like, well-studied problem. There has been some recent exciting developments. So I would say that, like, relevant algorithms for us are, like, for example, there is a very influential paper by QuadTree in 2013 who invented, well, actually, he didn't technically invent it, he adapted it to an optimal transport problem because it was invented back in the 70s. But basically, he does something which is called sinkhorn iterations. I'm not going to talk about it here, but it's some kind of, like, approach which is based on alternating minimization. We kind of compute like flow matrix, we first normalize rows, then columns, then rows again, then columns again, and so on and so forth. Yes, so linear scan may be too slow, yes, but we will see, sure, I will talk about it more. Yes, it can be, but that's already certain progress, and we will see later to what extent this is true, yes. Of course, you're right. And then the second class of approaches, actually like one of them was done in the same paper by Kushner et al. It's basically just based on very simple greedy algorithms. Like, for example, you can try to match each red point to the nearest blue point, right? Of course, what you will get, it's not a matching, but it's a lower bound for the cost of matching. And for example, in the Kushner et al. Paper, they kind of use this lower bound as a way to prune like irrelevant distributions for the nearest neighbor search. And then it was like refined by this other paper, and I'm sure there are other references. But yeah, so basically, these algorithms give us decent way of approximating Earth mover distance.
Ilya, sorry, I probably missed this. Can we have provable guarantee in the non-metric case?
Yes, for example, Sinkhorn iterations give you that. In fact, it converges to 1 plus epsilon approximation.
I see.
If you do enough of these iterations, yeah. Greedy doesn't have provable guarantees, but it works okay in practice, as we will see later. Yeah, okay, so now let's talk about metric case. Suppose now that we know that our red and blue points don't have arbitrary codes, but they actually come from a sufficiently nice metric, like is the case for our application with sentences, for example, right? So here, the game is to be fast. And what do I mean by fast? Even avoid writing the full matrix of costs. So I don't want to even compute distance between every red and every blue point. I want to be faster than that. And for that, I'm going to exploit my metric structure. For example, Kushner et al. Paper, they propose one very simple heuristic. It actually doesn't work super well, but it somehow works for them. So basically, we can just like, you know, if you have two distributions in Euclidean space, you can collapse each of them to the mean and use distance between means, again, as a lower bound for true EMD cost. This doesn't have any provable guarantees, and you can convince yourself, I wonder if shortest path first is good. So here, shortest paths are a little bit irrelevant because, okay, it's not an easy question to answer, so let me try to take it offline. So so basically, this collapsing these distributions to means is not, so you can invent easy examples to see that it's actually bad. If you want provable guarantees here, there is a classic algorithm by Indyk and Tapper back from 2003. Basically, algorithm is based on a QuadTree. And usually, if you talk to computational geometry people and think about QuadTrees and stuff, usually QuadTrees are useful for low-dimensional problems, and they kind of degrade as you increase the dimension. But for this problem, actually, QuadTree works perfectly in high dimensions, and I will convince you in that very soon. And I'm going to introduce QuadTree in detail in a couple of slides, because actually our paper more or less improves upon it a little bit. But for now, let me give you overall philosophy of what's happening here. So philosophy is that we take this metric, which is EMD cost between distributions, and it's a potentially very complicated metric. But let's try to embed it into a simpler space. So kind of like have some mapping from distributions to some additional feature vectors, and my EMD cost between distributions would kind of correspond to maybe L1 or L2 cost, just L1 or L2 distance between these feature vectors that we are going to construct. And specific way Indyk and Tapper approach this is if we have a metric, space M, it could be complicated, like it could be Euclidean space or something like this. Then they say that up to some factor, any metric can be approximated with a tree metric. And what is a tree metric? Tree metric is just shortest path metric on a tree, right? Something like this, like we have a tree with weights, and then, for example, distance between, do I have pointer in Zoom? Okay, it doesn't matter. So basically, distance between any points on the tree is just sum of weights along the edges between them. And so then in a certain way, they say that metric up to some log factor is a tree metric. Oh, you see my cursor, awesome. So for example, distance between this point and this point would be 8, right? Distance between this point is 5. Okay, so any metric is kind of a tree metric up to some factor.
Yeah, so we can also efficiently construct such a tree?
Yes, and QuadTree gives you one way of doing it, yeah. So it means that earth mover distance over my metric, it's kind of like earth mover distance over the tree, right? But earth mover distance over the tree, it can be represented in L1 space, actually without any loss. Again, like if it sounds mysterious to you, that's because it is. I'm not giving you any details. I will tell you more very soon. But just I want you to understand the high level picture. So basically we approximate a metric with a tree metric, and then we say that tree metric, EMD over the tree metric, it's actually very easy. And so it means that EMD over my general metric, it's kind of similar to L1 distance. So, okay, just to be clear, how we do it, I'm going to explain now, but this is the overall high level approach. And from computational point of view, this is awesome because, you know, like if we can have a function that takes our distribution into some feature vector, and for example, earth mover distance between these two distributions, it's kind of L1 distance between the feature vectors, it's a big win because L1 distances are much faster to compute than flows, right? So we don't need to compute any flow here. Okay, so now let me be slightly more specific. First of all, let me say that our main result is actually an improvement upon this QuadTree construction that Indik and Tapper introduced in 2003. We call it FlowTree. Not sure it's a very good name, but like it's stuck, so it is what it is. We do have like, so basically the trade-off we're obtaining is that it's much more accurate than QuadTree, but at the same time, it's not an embedding into L1 anymore. But at the same time, it's still faster than flow computation. So it's kind of like a little bit complicated trade-off, but we will see later that actually it gives us some net benefits. Does the tree depth relate to the accuracy of approximation? Yes, in a certain way. So you will see later that actually approximation depends on tree depth in a very precise way. Yes, linearly, in fact, with it. Okay, awesome. So before I'll talk about FlowTree, let me talk about tree approximations and QuadTree. Again, this is not our work, but this is what we build upon, and I think it's a good thing to know for everyone because I think these tree approximations are getting like second life these days. So the starting idea is very easy. We have some metric space. It could be complicated. It could be this like hyperbolic plane or whatever. And we would like to approximate it with a tree metric. And like the intuition is that trees are very easy. On trees, you can run recursive algorithm, like dynamic programming, whatever the hell you want. So, and like, actually, like if you think about it, it sounds almost like a stupid question to ask, right? Like, how can you possibly approximate a general metric with a tree? So let's consider a very simple metric space. Suppose that you have cycle of length n, right? And you consider shortest path metric over it. And then it's almost obvious, and in fact, you can prove it, that no tree approximation gives you any distortion better than n. If you cut your cycle anywhere, then you incur immediately very bad distortion. It would be factor of n. Turns out that the right definition here is to be randomized. So suppose that instead of cutting some edge, I cut a random edge in my cycle. And then if I cut a random edge, then expected distortion between any pair of points is just factor of 2. And factor of 2 is much better than factor of n. And turns out that you can generalize this intuition to general metric spaces. And originally this was done by Bartal in '96. And then there were many follow-ups leading to these two independent papers by Fakcherov, Rao and Talwar, and Gupta, Krautgamer, and Lee, who in 2003 proved an optimal bound. So basically, endpoint metric spaces can be probabilistically approximated by trees up to a log n factor. And this is tight. And this is a beautiful line of work. It has tons of applications. It has probably like hundreds of thousands of applications in theoretical computer science. But somehow, until recently, people didn't really perceive it as a very practical tool. Maybe that's what partially motivated question by Sasha about like efficient construction of these things. And you know, like if you see this log bounds, you start wondering like log bound, is it like good enough for practice or not? Or maybe like, you know, it's too pessimistic. So yeah, it kind of was perceived as like beautiful tool in theory, maybe not so useful in practice. Okay. So QuadTrees kind of change this situation a little bit. They do not work for general metrics, but they work for when your points are in a d-dimensional space, and when this d-dimensional space equipped with L1 or L2 norm, which is like probably covers most of the cases we care about in practice, so to say, with right definition of practice. Okay, so let me introduce the QuadTree now. So suppose we have a bunch of points, like for example, in this case, we have 3 points and we would like to, so we, for example, let's say we live on the plane. So we have 3 Euclidean distances between them, but we want to represent it as a tree for whatever reason. So here is how we do it. We enclose everything in a box of some, with some side length delta. And at the same time, we start building the tree simultaneously at the same time. So we consider the root, we build the root of our tree. Then we partition this into a bunch of boxes of half as big. And we recurse on the non-empty boxes. So for example, in this case, we have 2 boxes would be non-empty. So we build 2 children for the root. Okay, now for the child that has red point, we are done because we isolated a single point. And we keep partitioning the remainder. So basically, let's impose a grid of size twice as little. And we have only 1 non-empty child. And this 1 non-empty child gets split into 2 further children. And we have now isolated everything. So we are done. That's our tree that approximates the metric. So important thing here, there are like 2 important things here. First of all, the reason why people usually think about QuadTree being useful only in low dimensions, just because we have exponentially many boxes partitioning the big box. But here we recurse only on non-empty ones. And because we have at most n points, we can have at most n, non-empty children. So this actually scales well with the dimension. And the second important point, of course, in order to have any provable guarantees, we need to start not from fixed grid, but to randomly shift it. And the reason why it's important, suppose that you have 2 very close points, but you got unlucky and you split it at the first level of the tree. It can happen, right? If you start with any fixed position. And then it would be terrible because in the tree distance between these 2 points would be horrible. But if you kind of wiggle this grid at random a little bit in the beginning, then probability that you cut a particular close pair of points would be very low, right? Because you need to get particularly unlucky to do that. And you can actually analyze this. So again, in the original paper by Indyk and Tapper, QuadTree was actually analyzed in the low dimensions as well. Even though they kind of introduced the right algorithm for high dimensions, they only analyze it in low dimensions. So they kind of get bad dependence on the dimension. But later, in this paper by Andoni, Indyk, and Krautgamer, they analyze certain related algorithm, but you can easily see that you can change the analysis to analyze the QuadTree itself, and you obtain these bounds. So basically, in expectation, your tree distance for every pair of points is at most log times L1 distance between, original L1 distance between the points. And by the way, that answers your question about does the approximation depend on the depth? Because this d times delta is precisely the depth of this tree, where delta is like aspect ratio of our data set. We kind of assume that smallest distance is 1, largest distance is delta. Is the subgrid randomized at each level? No, just once initially. So as soon as we randomized the first grid, we just press. Actually, there are variants of QuadTree that do what you say, but like for our purposes, it's okay to just randomize it once. And from the lower bound side, we say that if we want to have a tail of size delta, so we want probability of underestimation to be at most delta, then we basically can achieve that as soon as we give a slack of like log 1 over delta. So it's pretty good. We kind of like lose a couple of logs and kind of approximate this L1 distance. And if you care about L2 distance, so one important lesson to learn is that L2 distance is L1 distance up to a random rotation. So basically, if you have L2 distances, just do a random rotation, and then on L1 distance, L1 distance between randomly rotated vectors is like close to L2 distance between the original vectors. So you can check this. So basically, yeah, like L2 distance, we can reduce to L1 by just random rotation. So this is it for the QuadTrees. But now let's see what it means for earth mover distance, right? So I told you how to approximate tree with a metric, sorry, metric with a tree, but now I need to explain you why earth mover distance over trees is easy. So, so if we have a tree, then actually finding perfect matching between red and blue points is actually almost trivial. In fact, it works for any tree, but it's particularly easy to see for our case, because in our case, tree is not just general tree, but it's very special because weights decrease exponentially as you go down. And then it's very easy to convince yourself that we need to match things greedily. So for example, in this case, we need to match this red point to this blue point. So we need to match as much as possible on the lower levels, just because higher levels cost us like exponentially more, right? And so we do this bottom-up greedy, and this gives us exactly optimal matching between any two distributions. And if you think about it a little bit more, so it might not be obvious that I'm saying it now, but like if you just pause and think for like 5 minutes, I can guarantee you it will be obvious to you that actually such a bottom-up greedy you can represent as just like L1 distance between certain auxiliary vectors. And the way you compute these auxiliary vectors is the following. So you just, your vectors, you have a coordinate for each node in the tree. And basically you put, like basically value of the coordinate is like basically scale of this level times amount of mass in the subtree. And you can compute two such vectors and compute their difference. And in difference, we will have non-zeros only how we should be matching things bottom-up greedily. So again, I'm not explaining it well, and it's not going to be super important for the subsequent talk. But let me just tell you that there is a very easy way to translate this problem of computing cost of this bottom-up greedy matching into just like writing down certain two vectors and computing their L1 distance. And what does it mean in terms of provable guarantees? So I told you already provable guarantees for the QuadTree, and they directly, almost directly, like it needs a little bit of work, but like it's very straightforward. So they translate into provable guarantees for Earth-mover distance. Namely, expected estimate for Earth-mover distance is at most Earth-mover distance times, again, the same log as before. But on the lower bound side, we need now to say that if both distributions are supported on S points, then we do not underestimate Earth-mover distance by more than log S with high probability. And the reason why we have log S now here, because we need to take union bound over all pairs of like S square points and use the second bound from the provable guarantees for the QuadTree. So that's roughly the provable guarantee we're obtaining. So again, like basically moral of the story is that we're estimating Earth-mover distance up to some logs, not super important which logs exactly. Okay, so this is like classic results. The construction itself was known back in 2003. Beta analysis of it was done in 2008. So what do we bring to the table? Okay, sorry. Before I go there, let me just like one last time summarize, just to, you know, like for those of you who prefer to stare at the slides and not listen. Basically, approximation to Earth-mover distance we're obtaining is like log support size times log dimension aspect ratio. But if you would like to solve nearest neighbor problem, then we need to compute n distances, not just one, right? And choose minimum. And in order to be accurate for all of these distances, we need to lose this additional log n factor because roughly speaking, instead of taking union bound over S square points, we need to take union bound over n times S square points. That's how we lose this additional log n. So this is the approximation we're getting for nearest neighbor search. So let me tell you what's our, like what do we bring to the table? What's our improvement upon QuadTree? And improvement is almost trivial. I actually, like when we thought of it, I couldn't believe that no one did it before. So the idea is we find the optimal matching as before. So we do the bottom-up greedy. But now, instead of computing the cost of this matching in the tree metric, let's compute the cost of this matching. Let's compute true cost of this matching in the original metric. So for example, we started with some points in the Euclidean space, then we approximated it with the tree, found matching there. But now cost of this matching, it's stupid to compute in the tree metric. So we should be computing it in the original Euclidean metric. And that's exactly what we do. That's the only change to the whole algorithm. So let's try to understand what it gives us. So there are like pros and cons to do that. And we will kind of argue that actually pros outweigh the cons in the end. So the obvious drawback of this is that it's not an embedding anymore. So I told you before, there is certain way to write down vectors such that this cost of bottom-up greedy matching corresponds like basically exactly equal to L1 distance between these feature vectors. But now, because we actually use original Euclidean distances, and the original Euclidean distances, they do not match exactly these three distances, it's not an embedding anymore. And this is a little bit of a problem, as we will see later. But on the positive side, we hope to be much more accurate, because like we will use tree just as a guidance. How should we match things? But we will be computing costs of the real thing. So, okay, so let me talk a little bit what it implies for theoretical and for empirical guarantees. So for theoretical guarantees, I told you that QuadTree gives like this log square approximation for individual distance computation. Then we lose this additional log n factor for nearest neighbor search when we need to compute n distances and choose the minimum of them. So we do prove a couple of theoretical results. First of all, we show that even for nearest neighbor search, when you need to compute n distances instead of 1, you do not need to lose this log n factor. And actually, like we see this both in practice and theoretically, but like in practice, let me talk about it a little bit later. But basically here, the idea is very simple. Like we use that FlowTree never underestimates Earth mover distance, because like it always computes some valid flow. It could be suboptimal, but fine. And then it computes its true cost. So we can overestimate easily, but we never underestimate. And this is great because we don't need to worry about, the only point we need to worry is about nearest neighbor. So as soon as we preserve distance with the nearest neighbor well enough, we're actually fine, because like far points are taken care of automatically. Is the loss of log n a real one? Yes, it's a real one. And I will talk about it in a second. It is very real. It's not artifact of the analysis. And then we also have some improvement. We show that basically you can get rid of dependence on the dimension and aspect ratio, and actually like just show a bound that is independent of anything except sparsity. So basically, if you know that your distributions are supported on S points, then you have a guarantee that it's like log square S approximation. We do not prove it in full generality. We kind of prove it. For example, we prove it for uniform distributions over S points, or when like granularity of your distribution is not too low. If you allow like tiny probability masses, this is probably just not true, actually. And we build on a certain trick, which again was done in low dimensions by Bachkors and Indik back in 2014, and we kind of generalize it to high dimensions for our case. Great. And okay, so now exactly what I was just asked. To what extent this is a real artifact, and to what extent this is a real artifact, or maybe we were just like sloppy with the analysis before. So we did some investigations, partially motivated by the fact that these polylogs are great, but like in practice, we want to be much better than polylogs. We want to find exact nearest neighbors. We don't want any like logs to lose, right? So we kind of cook up some distribution over instances. I'm not gonna tell you what it is, just like see the paper. But we kind of hand wave that maybe it models the real data a little bit better than the worst case. And there we kind of both theoretically and empirically show that FlowTree has a much higher probability of recovering true nearest neighbor than QuadTree. And this is an interesting thing. This precisely has to do with the question that you just asked me. FlowTree doesn't really degrade as you add more and more data points with respect to this distribution, but QuadTree degrades pretty rapidly, actually. So this log n is real. Oh no, delta is not constant. Basically, delta is aspect ratio not in probability masses, but on distances between atoms. So it's different. There are like two different parameters here. Delta is not constant. But like, for example, suppose that my aspect ratio can be arbitrarily bad, but I know that it's always uniform distribution over 10 points. Then our analysis applies. So we are not like cheating by changing the problem here. Okay, so we basically do have some beyond worst case analysis, both theoretical and empirical. But let me talk about like real empirical results and implementation in the last 20 minutes. I think they do tell some interesting story, these empirical results, as you will see. So we do implement our algorithm in C++, wrapping it in a Python wrapper so that both we and other people can use it easier. And we actually did spend quite a bit of time polishing this implementation to make it as fast as we can. So it's on GitHub. You are welcome to try to use it. For some of the baselines that rely on these matrix operations, like for example, sinkhorn iterations or greedy algorithms, we actually use NumPy with optimized underlying linear algebra library in order to be like as fair and as competitive as possible for these baselines. So in order to like get rid of as much like irrelevant variables, we kind of like restrict ourselves to just like evaluating on a single CPU core. So it becomes like, I think it's a great open question. What is really better if you allow many cores or if you allow GPUs or like other specialized hardware? But let's like be as clean as possible and just restrict ourselves to a single CPU core to like eliminate as many variables as we can. So what is the task that we're going to run our algorithms on? We pretty much just use this application from a Kushner et al. Paper. So we basically just want to retrieve k most similar text documents among n ones. So we also do have some experiments on images, but like I really think that these text experiments, they are more representative in some sense. And kind of like in this Kushner et al. Paper, we interpret text documents as uniform distributions over respective word embeddings. And for word embeddings, we just use these glove vectors, which is one of the standard state-of-the-art for word embeddings.
Ilya, just to make sure, so you ignore the kind of order of words in a sentence.
Exactly, we ignore the order. Yeah. So basically, if you have two sentences that are permuted, they would say the distance is 0. Yeah, good point. So for simplicity, let's assume that k equals 1. It doesn't matter too much. It was just like slightly easier for us. I think we also did some experiments with k equals 10, and it was kind of the same. Yeah, so there are like two types of experiments you might want to do. So the first kind is individual algorithms. So we kind of like have a bunch of baselines, and we have our new algorithms. So it's natural that there is a natural trade-off between accuracy and efficiency. The more accurate your algorithm is, the less efficient it is. On like one side of spectrum, there is like exact computation, which is extremely slow but perfectly accurate. On the other side, there are all these like simple things like let's collapse distribution to a mean and just compute Euclidean distance between means, right? It's like super fast, but it's, as you can imagine, not very accurate. And probably our new algorithm falls somewhere in between. So sure, I will show you these results. I think they do tell some story, but at the end, in order to understand whether we actually benefit from the new algorithms or not, we need to understand how this affects what's called pipelines of algorithms. So what are the pipelines here? So usually if you kind of run nearest neighbor search in practice, you almost never do it in one shot. You kind of have a bunch of algorithms that you compose together. And what I mean by this is the following. So like imagine that you start with a data set. Then you might use the first algorithm that prunes this data set to a certain number of candidates. Then you run the second algorithm that might be slower but more accurate to narrow it down. And then maybe you do it a few more times. And finally, you will use the exact algorithm that will compute you like nearest neighbor. And then your hope is that this true nearest neighbor didn't get filtered out in the first several stages so that exact algorithm can pick up on it. So that's how this is done in practice. And just like giving you a slight spoiler, we will see that FlowTree actually benefits of pipelines benefit from having FlowTree in it a lot. So basically, if you have any pipeline, just throw FlowTree in it and it will be better, roughly speaking. So what data sets do we use? So for text data sets, we use 20 News and Amazon. 20 News is some just standard data set in this literature of like some news articles, Amazon reviews. So someone asked me in the beginning of the talk, like we can avoid linear scan and it could be faster. Yes, this is great. But like the point of this, so this variant of the problem where instead of Euclidean distances, we do Earth-mover distances makes even much smaller data sets much more challenging. For example, if you have data set of size 10,000, Euclidean nearest neighbor, you would solve in just like, not even 1 millisecond. It would be probably like 100 microseconds or maybe even like less than that. But even such a modest data set is actually already pretty challenging for our problem when we compute nearest neighbors with respect to optimal transport. That's why actually just this like methods that are tailored for very large data sets, we are not even there yet. So we're still exploring, how to improve linear scan for now. But of course, the next natural stage, if you scale it up to like million points or billion of points, of course, then you wouldn't want to do linear scan. But at this scales, linear scan is perfectly adequate. We just need to speed it up. Individual distance computations should be faster than naive one. And yeah, like also for images, we use MNIST digits. Again, this is a standard benchmark for this literature. Let's not even spend too much time on discussing it. So what algorithms did we evaluate? So it's natural to split algorithms into 3 groups. So the first group of algorithm is this like fast linear time algorithms. So in particular, the QuadTree algorithm belongs to it. The mean algorithm, where we collapse distributions to means and compute distance between them, belongs to it. There are also 2 other baselines that I didn't mention. Let's not spend time on it, doesn't matter. On the opposite side of the spectrum, there are these non-metric algorithms where we write down the matrix of costs explicitly and do something with it, like greedy or maybe the sinkhorn iterations. So they're like slow and they're like quadratic time at least. So FlowTree falls in between. On one hand, it's much faster than these slow algorithms, but at the same time, it's noticeably slower than fast linear time algorithms, mostly because it's not an embedding. So instead of computing L1 distance, we need to do some work. We need to go over the tree, compute bottom-up matching, and do something with it. That's why. So it's kind of, you see, it falls in between. So the natural worry here, maybe it's like no man's land, right? Kind of like we are like less accurate than the slower algorithms, and they're like we are slower than faster algorithms. So is it good or not, right? So let's wait until we see the answer to this. But let's first start with individual algorithms and running times. So let me talk about running times very briefly. And the running times are what you expect. So there is a FlowTree, which is somewhere in the middle. And it's like, it takes some like hundreds of milliseconds. And then there are the slower algorithms, which takes seconds. And then there is this exact computation, which actually takes dozens of seconds. It's like very slow, even on this like relatively small data sets. And there are these fast algorithms. Fast algorithms work in some milliseconds. So it's basically like this intuition presented on the previous slide, it ends up being exactly correct. So now let's see what's the trade-off between running time and accuracy. So let me explain these plots. Let's start with the left plot. So what is the experiment that we are running here? We basically run given algorithm. So we basically compute estimate of the distance for each data point, like for each distribution in the data set. And then we say that if with respect to this estimate, I'll take top k candidates, for what fraction of queries these top k candidates will contain exact nearest neighbor? And naturally, the more candidates you consider, the higher probability that you hit the true nearest neighbor. But of course, it's better if our curve is to the left and to the top. So basically, it's ideal if we hit high probability considering very few candidates. And as you can see, for example, mean is the worst. It's actually not so good. In order to hit like 95% accuracy, you need to consider 2,000 candidates out of 10,000. So we do not prune that much. And as we basically use fancy and fancy algorithms, for example, QuadTree already ends up being pretty good. But then like more precise algorithms like FlowTree and others, they're like exceptionally good. They're so good that I need a separate plot for them to contrast them because they collapse in a single line on this left plot. So right plot precisely depicts FlowTree with more precise algorithms. So, and as you can see, FlowTree is very competitive with more precise algorithms while being much faster. So basically, instead of running for like some seconds, you can be done with like 0.25 seconds, something like this.
To clarify, is the query an entire document or just like a search query?
Yeah. Query, like, so dataset, basically datasets consists of text documents, and query is also a text document. So we just retrieve news articles that look the most similar to a given one. It's not a single word, but it's a whole like paragraph of text or whatever. So the same happens for Amazon.
So, but if the data set becomes larger, FlowTree doesn't seem to perform very well.
Right, but yes, but wait until the next slide. I'll talk more about it. Yeah, okay, great. So for Amazon, it stays the same. So FlowTree is competitive with slower algorithms while being much faster. So it's like 100 milliseconds instead of like whatever, almost a second. For MNIST, it's kind of the same. Let's not waste time on it. So let's talk about pipelines, and that's what will answer your question that you just asked me. So let me remind you what pipeline is. So it's basically, again, like I already told you, let me just repeat so that we are still on the same page. We start with a whole data set, pass it through first algorithm, and gives us list of candidates. And then we narrow it down to the smaller list, and we do it potentially a few more times until we actually use the exact algorithm. We don't have to use exact algorithm, by the way, always. Sometimes, as we will see, we don't even need it, and we're still okay. So there are like two questions here: which algorithms to use and how to tune numbers of candidates, right? So basically, we did two experiments. We either return one document or 5 documents, such that the true nearest neighbor is among them with probability at least 90%. Sounds like a reasonable requirement, and I think, yeah, well, okay. And we kind of do it just for a single data set. I think we also try it for other data set. It was kind of the same. So the lessons we learn is exactly the same. We just do it for 20 news. So let me first start with the punchline here. So basically, in both cases, for like recall at 1 and recall at 5, we see significant improvement of the running time for pipelines with FlowTree compared to the best pipeline we could find without FlowTree. So for example, for like recall at 5, especially the gap is big. It's like, I think, factor of 8 or like factor of 7 or something. I'm bad at like doing math at the spot. But also the gap is significant for recall at 1. So now let me be slightly more nuanced. The way we organize pipelines are the following. So as a first algorithm, we use some very fast algorithm that will allow us to prune the whole data set to a subset. So it could be mean, QuadTree, or some other baseline, not important. By the way, answering your question that you just asked me, if in reality we will have a truly large data set, we will just use as a first step something, for example, sublinear that doesn't do linear scan. And then after we do this pruning, we use FlowTree to narrow down this list of candidates. And sure, if your data set would be truly huge, if you just do FlowTree, it might be slow and performance would not be good. You are right. But my point is it will be good as a part of pipeline. So we first use some kind of maybe indexing based on some like locality sensitive hashing or something like this, or like some graph-based methods or whatever is in vogue these days. But my point is FlowTree is very, very useful as some intermediate stage of the pipeline. And that's what these experiments show. Did I answer your question? Well, I did actually. So let me for now move on, and yeah, maybe we can have a more discussion later. So after we do this fast algorithm that does a little bit of pruning, we use FlowTree to prune it further, and then we potentially use slower algorithms to prune it further, and then use exact algorithms. So we kind of have a whole profile of algorithms here. And actually, our experiments show pretty convincingly that QuadTree is the best first algorithm. So basically, doing the QuadTree embedding and then computing L1 distances between feature vectors, it works the best as a first step. It's much better than mean or other baselines. And again, like we noticed that FlowTree always improves things. Like every pipeline you can try, add FlowTree to it and it will be better. And I think the same will stay for extremely large data sets where just FlowTree would not be necessarily as great. And exact algorithm is not always necessary, just because, for example, if previous algorithms already did a good job and narrowed it down to 5 points, you know, we don't really insist on running exact algorithm that much. And here are the precise results. So let me try to explain what's going on here. There are like quite a few things on these plots to unpack. So the left plot is for when we return 1 document, the right plot is for 5 documents. They're kind of similar, so let's focus on the left one where we return 1 document. So basically, each bar is a pipeline. And we subdivide the bar according to how much time each component of the pipeline takes. So for example, this pipeline consists of QuadTree. This is the first part. And then we do some greedy. This is the second part. And then we do exact computation. This is the third part. And for example, this is what happens if to this pipeline you add FlowTree and retune the parameters. Basically, FlowTree eats away almost all the time that is consumed by the greedy algorithm. So it basically does the pruning. We still need a little bit of greedy, but like it's much faster than before. So we run it on much fewer candidates. And this happens consistently across the board. Moreover, for example, when you return 5 neighbors, the best pipeline we end up having is just QuadTree plus FlowTree, and that's it. We don't even need exact. And like, as you can see, actually, here, many pipelines do not have exact algorithm running it. So, yeah. Yeah, so basically that's the point. FlowTree improves things always. And pipelines, actually optimal pipelines consist of quite a few algorithms. Okay, we're almost done. So what's the key takeaway? The reason why I got excited about this problem is that it kind of like, so I worked a lot on nearest neighbor search for Euclidean distance. I spent more or less like big chunk of my PhD on that, and I'm still very interested in it. But unlike classic Euclidean k-nearest neighbor search with respect to these more exotic distances, I mean, they're not really exotic, but they're obviously like more exotic than Euclidean. Nearest neighbor search exhibits here a much diverse efficiency accuracy trade-off. That's why actually optimal pipelines consist of quite a few steps. And roughly speaking, the reason for this is that because we can afford very few exact distance computations just because they're so expensive. For example, for the time our whole pipeline runs, we could have computed only maybe 5 exact distances. So that's why this preliminary pruning becomes particularly important. And this is not really the case for Euclidean case. For Euclidean case, these data structures start shining when your data set is very big. But for example, for million points, there is almost no point in using it. You can just do linear scan and be okay with it, especially if you run it on like GPU or whatever. So that's why this problem is much more interesting, both like mathematically and computationally. And yeah, so just to conclude my talk, I have two more minutes left. So in this talk, we introduced FlowTree, which is a simple but very effective modification of the classic QuadTree for estimating the Earth mover distance in high dimensions. And it yields better theoretical and empirical results. And theoretical results, we have both worst case and beyond worst case. And we do have publicly available implementation, which is like C++ code with a Python wrapper, which you can download on this GitHub link. And actually, like every time I put up some code online, it amazes me how much work it is. So basically, in order just to make sure that it compiles and builds in different environments and like reasonably well tested, and we're like fairly confident that it will not blow up your computer. It actually took us like maybe as much time as actually writing it in the first place, writing these implementations. But yeah, you can try it out for your application, or just, you know, if you invent better algorithm. Yeah. So yeah, okay. So with this, let me conclude my talk. If you have any questions, you can ask them now. So one question I see: what are possible applications of FlowTree? So basically, anywhere where you need this k-nearest neighbor retrieval with respect to Earth mover distance, you can use FlowTree to speed it up. Why would you need that? For example, if you want to do k-nearest neighbor classification with, for text documents, and like some of these previous papers actually argued that this is a very good similarity measure. And actually, I know some NLP people at Microsoft who also use Earth mover distance for some tasks. I don't think their data sets are big enough to actually even like require what we developed, but you know, like we're always building things for the future. So yeah. Can you give some intuition on the log square S approximation? Where does the second log S term come from? Okay, it's a great question. It's not very easy to explain, but let me try. So the short answer is that one log S comes from the fact that we just lose a log. And second log S comes from the fact that instead of embedding into L1, this will be embedding into L1 minus epsilon for a very small epsilon. And this second log comes from the fact that by changing our space between L1 and L1 minus epsilon, we lose this log. Again, we can have a more detailed discussion offline, but that's very roughly the reason. So yeah, like, okay, any more questions? Otherwise, we can call it a day.
Let's thank Ilya. Okay. Yeah. Thank you, Ilya. Great talk.
Okay, cool.
Let me stop recording.